Namaskar from the Department of Biotechnology and I roll number is 009. Today I am going to present you the topic that is working of infrared spectroscopy. Here are the table of contents, summary, history, introduction to IR, details, applications, and conclusion. Starting with the history, infrared radiation was discovered in 1800 by astronomer Sir William Herschel, who discovered a type of invisible radiation, the spectrum low in energy than red light, by means of its effect on a thermometer. Slightly more than half of the total energy of the sun was eventually found to arrive on Earth in the form of infrared. The balance between absorbed and estimated infrared radiation has a critical effect on Earth's climate. Infrared radiation is emitted or absorbed by molecules with a change in their rotational vibrational moment. It excites vibrational modes in the molecules who are changed in the dipole moment, making it a useful frequency range for study of these energy states for molecules of the proper symmetry. Infrared spectroscopy examines absorption and transmission of photons in the infrared range. So let's get started right away with probably the most important question: what is infrared spectroscopy? Basically, infrared spectroscopy studies interaction with ion radiation and matter. Well, in this presentation, you may ask what IR radiation is. Well, IR is a particular part of the EM spectrum, that is electromagnetic spectrum, that is longer wavelength from visible light. A long wavelength means light carrying less energy. It also means a small wave number. Infrared spectroscopy is not created equal. It can be subdivided depending on wavelength into near, mid, and far infrared. Into near, mid, and far infrared. Although most mid-infrared is meant when the term IR spectroscopy is used. As mentioned before, infrared light interacts with matter, but how exactly? Well, first infrared light passes in the sample. Mm, yeah, as mentioned before, infrared light interacts with matter, but how exactly? Well, first infrared light passes the sample. In our case, it is an exemplary water molecule, depending on energy level. This light can trigger vibration and specific molecular bonds, which is called absorption. There are different kinds of vibration, but most prominent are symmetric stretching vibration, symmetric stretching vibration, as you can see in the diagram, antisymmetric stretching vibration, deformation vibration, and the common are rocking, waving, twisting vibration. The energy absorbed by molecule is consumed and therefore missing from the original IR field. But how we can use this process for our advantage and investigate this interaction? First, we use infrared light from a fixed source. The light is then directed at the sample. Some light is going to be reflected, but larger section is going to travel through the sample and specific part of it are going to absorb by the sample material. The part of the light that is transmitted and carries some molecular information of sample can then be collected by the detector to produce an electronic signal. But how do we turn this electronic signal into a spectrum? Well, this depends on how IR spectrometer is set up. As you can see my explanation in this diagram. This can be explained by traditional dispersive spectrometer. This was done by the directing light on a diffracting plane that splits light into several signal streams. Afterwards, these beams were directed at the sample and each wavelength is individually examined. Now I'm going to show the clear working of dispersive spectrometer. As the name suggests, a dispersive spectrometer creates spectra by optically dispersing the incoming radiation into its frequency or spectral component. As illustrated in the figure, common dispersive elements include prism and gradient. Dispersive spectrometers can be further classified into two types, monochromates and spectrographs. A monochromator uses a single detector and narrow slit and a rotating dispersive element allowing the user to observe a spectral range of wavelengths. Well, the figure below shows a simplified schematic diagram of a monochromator. A photograph of an uses an array of detector elements and a stationary spatial element, in this case, it will turn the figure is removed and spectral elements over a wide range of wavelengths are obtained in the same time, therefore providing faster measurements with more expensive detection systems. Now here comes the working of our dispersive spectrometer. First, we'll start the radiation source in geological heating. It will produce higher radiations. The radiation will go towards the mirror M, which reflects half of the radiation towards the M1 and half of the radiation towards the M1 dash, as you can see in the figure, towards the M1 and towards the M1 dash. Okay. Then M1 will reflect radiation towards the reference mirror and radiation will pass from the reference material without decreasing in the intensity of the IR radiation. At the same time, mirror M1 dash will reflect the radiation towards sample web. Some radiation will pass from the sample and some radiation will be absorbed by the sample. The intensity of the passed radiation will be decreased. The radiation which is the beam chopper, it will also represent the reference and the sample radiation to the mirrors M2 and M2 dash and finally M3 before then taking reference radiation for deformation. This mirror will send reflected radiation towards the slit S1 and then it goes to the diffraction grating. Grating will diffract the radiation so resolution will be improved and these reflected radiation will be passed through slit S2. Slit S2 will allow the radiation only in range of 4000 to 400 centimeter intervals. These reference radiation will reach to the detector and detector will analyze the intensity of the radiation. The chopper will send the sample radiation at that time. Reference radiation will not reach the detector. The sample radiation will follow the same steps and it will reach the detector like this. And this process continued throughout the analysis. Finally, detector determines which frequency have been absorbed by the sample and which are unaffected. Intensity of absorbed radiation will decrease and remain amplified by the amplifier like this and finally IR spectrum is visible in the recorder. As you can see the detail in this figure. In IR spectroscopy, the spectrum will appear in terms of percent transmittance versus wave number. The second type of infrared spectrometer used in infrared spectroscopy is with the rise of improved electronics and CPU processing, or Fourier transform infrared spectrometer (FTIR) is used. FTIR stands for Fourier transform infrared, the preferred method of infrared spectroscopy when higher radiation is passed through a sample, some radiation is absorbed by the sample, and some passing through is transmitted. The resulting signal at the detector is a spectrum, resulting a molecular fingerprint of the sample. The usefulness of infrared spectroscopy arises because different chemical structures, molecules produce different spectral fingerprints. The center of FTIR spectrometer is a Michelson interferometer. During the measurement, IR beam enters the interferometer and is directed at the beam splitter. Now, discussing the detail, I will show you detail by showing this figure. The hard-effective spectrometer is an interferometer shown in the figure on the right is a Michelson type interferometer. During the measurement, beams enter the interferometer and is directed at the beam splitter. As the name suggests, this splits the beam into two separate beams that are directed to a fixed moving mirror respectively. When light travels back to the beam splitter, where it is recombined, causing interference and is then directed to the sample material. That's why spectrophotometer of all wavelengths can be acquired simultaneously, saving a lot of time. At the end, the detector produces a raw signal of light intensity versus mirror position, but how do we get from here to the classical IR transmission spectrum? To get nice and clean sample spectra, we have to get the nice and clean from the spectra, we have to get rid of environmental influences that may be shown in our spectra like CO2 or the water vapors. To do that, we first need to measure spectrum without a sample present. This raw signal is then mathematically fully transformed into classical IR plot of intensity versus wave number. We now have a signal channel reference spectrum. Then we insert the sample into beam and repeat the process. FTIR then yields another single channel, but this time it is a sample spectrum. There we only have to combine both spectra by dividing sample spectrum sample spectrum. They will only have to combine both spectra by dividing sample spectrum by reference spectrum, and then we have classical view of FTIR transmission spectrum. But what can we do with it? A lot of things actually. You can see this process. After dividing, you can get this. The procedure is repeated with the sample present, yeah, and the sample spectrum is then divided by reference spectrum to find the transmission spectrum. Now coming towards the application of FTIR spectroscopy. An FTIR is like a chemical fingerprint. This enables chemical identification of a variety of samples and frequently used to characterize material properties and verify known and elucidate unknown samples. It is utilized for many industries but especially useful when chemical information needs to be obtained straight away straight away in short amount of time. FTIR is extremely versatile depending on your spectrometer setup and measurement techniques used. Many of its applications are feasible and many theoretical questions are answered. Thank you for your time and attention.